Niels Bohr lived from 1885 to 1962, and the calculation that we're going to follow he did in 1913, and it was what he won the Nobel Prize for in 1922. He developed the Rutherford model into what we now call the Bohr model of the atom, where basically still we have a positive nucleus with, say, an electron kind of orbiting around the nucleus. But what happens? The electron can start out in a higher energy level, in other words, in an orbit where it's further away from the nucleus, and then if it drops down to a lower energy level, in other words, it drops down to a lower orbit where it's closer to the nucleus, kind of like dropping from a higher stair on a staircase to a lower stair. When it does that, it's got less energy down here, so what happens to that extra energy when it drops down? That energy is emitted as a photon. So all of those photons, all of that light that we see in the hydrogen discharge emission spectrum are all from electrons dropping down from one level to another level. Now, why do we only get certain energies of photons? Well, perhaps it's because the electrons can only have certain energies in their orbits. If the electrons are limited to only certain orbits, then they could only give off the energy differences between those orbits, which would only be certain energies for the photons. Well, let's take a look at an electron going around a nucleus, and what we're going to do is we're going to look at what's called a hydrogen-like atom. A hydrogen-like atom means an atom with only one electron. So pick whatever element you want. We'll assume we have Z protons in the nucleus. In other words, we're going to look at an element of atomic number Z, so there are Z protons in the nucleus. But imagine that we strip off all of the electrons except for one. We're only going to leave one, and then we're going to look at how that electron will go around the nucleus. Great. That's what we're going to do. Let's take a look. So, let's imagine we have this electron that is going around in an orbit around the nucleus. The nucleus, we'll assume, has a charge of plus Ze, Z protons for atomic number Z. Each proton has a charge of plus E, one electrostatic unit. So the charge on the nucleus is plus Ze. The charge on the electron is minus E. There's going to be an electrostatic force of attraction between the two. That will act as a centripetal force, keeping the electron in orbit around the nucleus. So what do we have? We have the magnitude of the force, the magnitude of the electrostatic force is K magnitude Q1 magnitude Q2 over R squared, which will be K, charge on the nucleus is Ze, charge on the electron, absolute value is E over R squared, or Kz E squared over R squared. Now that must equal the centripetal force, which is mv squared over r for the electron, where m here is the mass of the electron. Solving for r, we'll multiply by r squared, that will cancel one of the r's, divide by mev squared, and we get that r is kze squared over mev squared. That is the radius of the orbit in terms of these quantities dealing with the motion. Now this is a classical result. What did we use here? Classical electrostatics, classical mechanics for the centripetal force. So our result here for R is a classical result. Now let's take some quantum mechanics into account. This electron, we know, has a wave-like nature. It's not just a little ball going around orbiting the nucleus. It's got a wave-like nature. So how are we going to take that wave nature into account? Well, the electron is kind of fixed in this particular region, the region in the orbit, say the circumference of the orbit, which is 2 pi times r. Well, what happens when waves are restricted to a particular space? Well, last semester we looked at standing waves, and we saw that there were different kinds of standing waves. If I have a wave, say, trapped between these two ends, we could have a standing wave that was made of, say, one hump, like this, or at a higher frequency, we might have a wave This is very hard to do with my hands at the, like this, with two, hold on, try that again. There we go, kind of, with two humps. There we go, with two humps. Try it with three humps. Okay, that is working absolutely horribly. Okay, but I think you get the idea. We can have only certain numbers of waves in our fixed region. We might have, say, one hump that oscillates back and forth. We could have two humps that oscillate back and forth. We could have three humps that oscillate back and forth. Okay, etc., etc. Now, in this case, we've got an electron in this fixed length of orbit with a length of 2 pi r, 2 pi times the radius of the motion. Perhaps we have a very similar sort of situation. Maybe the electron can only have either one wavelength in that distance, or two wavelengths, or three wavelengths. Well, that would create a quantum mechanical restriction to only those certain kinds of waves, only those certain kinds of orbits that would allow a certain number of waves to fit in it. Well, what happens in that case? So if we make this restriction that the circumference of the orbit, which is 2 pi r, has to be a counting number, 1, 2, 3, 4, number of wavelengths. Now here, n is going to tell us the number of wavelengths that can fit in our orbit. If n is 1, then we have 1 de Broglie wavelength fitting in the circumference. If n is 2, we have 2 de Broglie wavelengths. So n tells us the number of de Broglie wavelengths of the electron that will fit in the circumference of the orbit. Now remember, the de Broglie wavelength is h over p, where we're talking about the momentum of the electron, and p is mv, so we have that 2 pi r is nh over mev. Multiplying by v divided by 2 pi r, we have that v, the velocity of the electron, is equal to nh over 2 pi r me. Let me just emphasize that v is the velocity of the electron as it goes around its orbit, just like we had up here for the centripetal force. Now, we're going to take this result for v and put it into this equation here for our classical result for the radius of the orbit. This is going to give us a quantum mechanical restriction. So this is our classical result. This is a quantum mechanical restriction that we get by assuming we can only have a certain number of wavelengths in our orbit. We're going to put these together by taking this result for the velocity, putting it in here, which is going to give us an equation with r on the left side and r on the right side. I'll solve that for r, and then we'll find what r is in terms of these other quantities. Taking v and putting it up into here, we have then that r equals kze squared over me times 1 over v squared. Taking this, flipping it upside down and squaring it, we get 4 pi squared r squared me squared over n squared h squared. Dividing both sides by r, one of the r's will cancel, and multiplying everything else to the other side upside down, we find r is equal to n squared h squared over 4 pi squared mekze squared. Now, just to make this a little bit easier, there's another value that's referred to as Planck's constant, but it's referred to as h bar, where h bar is h over 2 pi. So I can actually remove this h squared over 4 pi squared and write that as h bar squared. So it makes it a little bit easier. We have h bar squared over meke squared, and then also times n squared over z. And that is r. That is the equation which describes the different possible values for r, the radii of our orbits. Now notice that r depends on h bar, me, k, and e. Those are all constants. The only things that can change in this equation are n and z. So notice you pick whatever atom you want, whatever element you want, you put in your value for z, and then the radii of the orbits go as n squared. They increase by n squared. There's a particular value of this that's kind of useful. It's called the Bohr radius. And it is the smallest value for hydrogen. So if we put in z equals 1 for hydrogen and n equals 1, if we just put in all of these constants here, that will give us the value of the Bohr radius. And it turns out that that value is referred to as R1, and its numerical value is 5.29 times 10 to the minus 11 meters. So that's the Bohr radius. It's the smallest radius for an orbit in hydrogen. We can then think of this equation basically as R equals n squared over z times R1, times the Bohr radius. So notice that as we look at larger and larger atoms with more and more protons in the nucleus, the radii get smaller and smaller. If we were to look at helium, where n equals 2, all of the radii are half as large as the radii for hydrogen. If we were to look at lithium, they would be 1/3 as much. So, as we get larger and larger values for z, the radii get smaller and smaller. But as you go to larger and larger values for the orbits, they increase by n squared. So for hydrogen, the lowest orbit is R1. The next orbit is 4R1. The next one is 9R1, then 16R1, 25R1. So the radii get large very, very rapidly. Keep in mind that as we increase n, we're increasing the number of wavelengths that will fit in those radii. Okay, in those circumferences, in those orbits. Okay, very, very good. Now, we're not just looking for the radii. We would like to know what are those energy differences for those orbits. That's what we were originally thinking about when we were talking about the photons that were emitted. So, what are the energy differences between the orbits? The total energy of the electron going around in the orbit will be a sum of its kinetic energy plus its potential energy. The kinetic energy is 1/2 mv squared, mass of the electron again, and the potential is electrostatic potential. Remember, electrostatic potential is K Q1 Q2 over R. So K Q1 ZE, Q2, now we're not looking at the absolute value here, this is a scalar, so we want the real charge, which is negative E, over R. So what do we end up with? Well, we're going to take V, which we got last time, earlier, before, of NH bar over RME. We're going to put that in for V squared. At the same time, for R, we're going to replace R with the other equation we had, H bar squared over MEKE squared times N squared over Z. So what do we get? We get 1/2 ME V squared. Now what's V squared? V squared will be N squared H bar squared over ME divided by R squared. So we're going to invert R and square it to give us ME squared K squared E to the 4th Z squared over H bar to the 4th N to the 4th. So we flipped that over and squared it. Then minus KZE squared, minus KZE squared, divided by R. So again, we need to take R, flip it upside down, MEKE squared, Z over H bar squared, N squared. Now, let's notice here we can simplify a bit. We have an H bar squared, and we can cancel 2 of those. We have an N squared, we can cancel 2 of those. We have an ME squared and ME squared. So what do we end up with? Notice we have 1/2 ME, well there's an ME, K squared, K times K, K squared, E to the 4th, E squared, that's E to the 4th, Z squared, Z times Z, that's Z squared, divided by H bar squared, N squared, N squared. So we've got the same group of constants, except here we have 1/2 times that, and then minus 1 times that. Well, 1/2 minus 1 is negative 1/2. So we have negative ME K squared E to the 4th Z squared over 2, 1/2 minus 1, the negative 2, h bar squared n squared. There we go. So that is the energy of the electron going around in the orbit. Now let's imagine that we start out at some initial value of n initial for our number n here. And then we drop down to some lower value n final. Remember, we're expecting that the energy of the emitted photon to be the difference between those energies. In other words, the energy of n initial minus the energy of n final. That will be the emitted energy of the photon. So let's take this value for the energy with some amount for n initial and then subtract the energy with this for n final. And that should be our energy of the emitted photon. So the energy of our emitted photon, which remember is hf, or with F equals c over lambda, we could write this as hc over lambda, is going to be equal to the difference in the energies of the electron. In other words, the initial electron energy minus the final electron energy. You might think, well, isn't the change in energy always the final minus the initial? But the photon energy is the amount that's being lost by the electron. So it's actually the initial minus the final. That's what we'll get for the emitted energy. So En initial minus En final, well, using the equation that we just had from the last board, that'll be that preliminary constant, z squared me k squared e to the fourth over 2h bar squared times, so the initial one will be negative 1 over n initial squared, and then minus the value with n final, and that's negative 1 over n final squared. Well, we have minus a negative, this gives us plus. So we can write this whole thing then as, if we divide off the hc, we'll have 1 over lambda equals z squared me k squared e to the fourth over 2h bar squared, dividing the hc, we have hc, times 1 over n final squared minus 1 over n initial squared. Now let's stick values in here. Well, we've got mass of the electron, 9.11 times 10 to the minus whatever, K, 8.99 times 10 to the whatever, E, 1.602 times 10 to the minus whatever, divided by all these things. Put all those numbers in, and what do we get? It turns out we get 1.097 times 10 to the 7th inverse meters. What's that? It is the Rydberg constant. So what do we get? We get 1 over lambda is equal to z squared times r times 1 over n final squared minus 1 over n initial squared. Not only do we get exactly what we found for hydrogen, just put in z equals 1 and we have exactly the result that we found for hydrogen. We have an even more general result that can be used for any, remember, hydrogen-like atom. So any atom that only has one electron, where we've stripped all the other electrons off and left only one, we get a very similar equation to the hydrogen equation. All we have to do is multiply by the atomic number squared, by z squared. Very, very good. That is an amazing result. Now, I don't expect you, now I'm speaking to my class, I don't expect you to be able to reproduce this, but I really do hope that you understand all of the steps we went through. There was a lot of algebra in there, but I hope you understand the steps, and what I really want is for you to be able to use the results that we have gotten. Now, I'm going to stop there for this lecture, and the next lecture we'll basically look at some applications of this, and that's going to be our last lecture for Physics 1112. So, I hope you enjoyed this lecture. I'll see you next time.